Hi guys, this is Mrs. Foy, and this is a screencast about how to read a manometer and a little bit about phase changes. So, reading a manometer is a way to calculate the gas pressure of a gas. And the way that it works is that it has a tube that is open to atmospheric pressure. And we've learned before that pressure is actually collisions, right? It's the collisions on a container of the gas molecules bombarding it. So you can think of atmospheric pressure of the gas molecules in the atmosphere pushing down and bombarding this area. And this would be the level A, right? So the pressure from the atmosphere is pushing down. But we also have the gas pressure of the particles in this gas that are pushing, in this case, up. You can think of it as pushing it up, which in this case is actually going down here the way this tube is. And so if the atmospheric pressure, the pressure of the atmosphere, was pushing at the same pressure as the gas in this container, then level A would be equal to level B. So you can kind of think of a manometer as a tug of war. You can also think of it as like a seesaw, where both pressures are working against each other as they push on this, what is usually mercury, right, which is a very dense liquid. And so here I can tell in this picture that the atmospheric pressure must be higher than the pressure in the gas, right? So the atmospheric pressure is winning the war, so to speak, right? So it's winning that tug of war. And we can actually calculate how much more it is winning. So in this particular case, what we have here is we have the level A is, as we said, higher. And how much higher? Well, it's pushing 30 millimeters of mercury more. And so what I can say is, since I know atmospheric pressure is 750 and it's pushing 30 millimeters of mercury more than the gas, then the gas must be 720 millimeters of mercury. So let's take a look at what we have here. All right, so we've got some manometers. The first thing that I like to do is I like to go and see who's winning the tug of war. Here I can see that the atmosphere is winning, right? So the atmospheric pressure here is winning. Here I can tell that the atmospheric pressure is winning. The atmospheric pressure is winning here. It's pushing down more. And on the last picture, I can tell that the gas pressure is winning because it's actually pushing this way, and so it's actually higher. So let's see if we can calculate exactly get a quantitative measure of this gas. Here, this is neon, all right? So it's telling me that atmospheric pressure is 773, and I know that it is, in this case, greater than the neon, right? It's greater than the neon. Well, how much greater? Well, it's 8 centimeters greater, which I can calculate to 80 millimeters. And so then I would say, well, I know that the neon is less, so I would take 773 minus 80 773 millimeters of mercury minus the 80 millimeters of mercury, and that would get the neon gas at a 693 millimeters of mercury. All right, let's look at this one. In this picture, I can see that the atmospheric pressure is also winning the tug of war, right? So it's pushing down on that mercury more. So in this case, I don't know what this gas is, but I know that it is going to be greater. Well, how much greater? Well, I can see that the atmospheric pressure is 763. The pressure of the atmosphere is 763. And I know that the difference of where it should be, this delta H, right, is 35 millimeters. And so that means the gas, whatever gas is in here, this pressure of this gas must be 728 millimeters of mercury. Millimeters of mercury. All right. In this picture, I can see that the gas is greater than the atmospheric pressure. So whatever this gas is, it is pushing greater. How much greater? Well, it's going to be H, right? The delta of what it would be that if they were equal, which is 24 millimeters of mercury. And so in this case, I would take the gas pressure, which is 765, and I would add the 24 millimeters of mercury. And so I would get the pressure in the atmosphere of 741 millimeters of mercury. So this is what we call a phase change diagram. And this is looking at the temperature, and it's looking at kind of a crude cartoon of what the particles at each phase look like. So I can tell this is a solid, I can tell this is a liquid, and I can tell that this is a gas. So what I'm looking at here is I'm looking at the name of the transition between solid to liquid. Well, if I go from a solid to a liquid is melting. And if I go from a liquid to a solid, that's freezing, right? If I go from a liquid to a gas, is boiling. And if I go from a gas to a liquid, that is condensation. Condensation, right? So if we were actually doing, if we were in school and we were doing this lab, and hopefully you will get to see this, what actually happens is if you had some ice, right, and you were heating that ice in a test tube, and you were monitoring the temperature, what would happen is the temperature would go up, 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 up as you added more heat. But at a certain temperature, what would happen is that you would see this temperature level off, like a little level. And at that point, even though you are adding more heat, the temperature does not go up. It stays level right there. And that's when you know that that is what we call the freezing point, melting point, because that energy that you're adding is actually going to break the intermolecular bonds between the solid and the liquid and freeing those so much so they become a liquid state. And then if you added more heat, you would see the temperature start to go up again, where it's going up, going up, going up. And then at a certain point, depending on what the material is, again, even though you're adding more heat energy, you would see the temperature level off. And it's very strange because you're like cranking that Bunsen burner, but the temperature levels off. And that is because the energy that you're putting in is going to completely now break those intermolecular forces, and the liquid turns into a gas phase. And at that point, the temperature would rise up again. So where it gets level, this would be the boiling point, condensation point. Where it gets level here, this would be the melting or freezing point. There is also another phase change difference, and this one we don't often see with materials that we work with usually at the temperatures and pressures that we usually do. But there is a way of going straight from a solid to a gas, and that's called sublimation. So if you've ever were lucky enough to play with some dry ice, you've probably seen that. There's just no liquid. You put a piece of dry ice, which is solid CO2 or dry ice, and what happens is it goes straight from a solid to a gas. The tabletop would not be wet at all. The other phase change is just the opposite. So if it goes from a gas to a solid, that's called deposition. And you would just kind of skip over the liquid phase. And sometimes on super, super cold mornings, you can see a deposition occurring like frost on a window pane. So what is the boiling point of water? And you might say, I know that, Mrs. Hoy, it's 100 degrees C. But is it? Is it always 100 degrees C? So let's talk about that. if you've ever had a chance to go up into any high altitude, like in Denver, Colorado, if you look, you're going to make some Kraft macaroni and cheese. It will actually say that you need to cook your food longer. You need to boil those noodles longer. And why is that? Well, Denver, here's my mountain peak here, okay? Denver is actually a mile higher than York, all right? So it's approximately 1 mile higher. Now, I'm assuming that York is at sea level, and it's not really, but it's kind of there. So in Denver, we are 1 mile higher. So the way you can think about this is that we have so much more gas pressure pushing on us in York than in Denver. So there is less gas or less atmospheric pressure in Denver. And so because of that, if you're trying to boil water, you have less atmospheric pressure pushing on your liquid when you're in Denver than you do in York. And so in Denver, water boils about 95 degrees C, whereas in York, it boils about 100 degrees C. And so when you're cooking your macaroni and cheese, you're only, the water's boiling, but it's only 95 degrees C. And so that's why you actually have to cook it longer, because it's not quite hot enough. So now we're going to look at these really cool diagrams called phase change diagrams. And what it does is it displays the phases of the substance at certain pressure and certain temperatures. So pressure is always on the Y and temperature is always on the X. And so along these black lines that you see, two phases exist. And you can see that between A and D, I have a phase between solid and liquid. Between A and B, I have a phase between liquid and gas. But there's one set of conditions, one set of pressure and temperature, where all three phases meet. And this is called triple point. So right here I can see I've got the solid, liquid, and gas all at one point. So what is triple point? This is the pressure and the temperature at which a substance has some of the molecules in a solid form, like this, some of the molecules in a liquid form like this, and some of the molecules or atoms in a gas form like that. And hopefully we'll soon be doing an experiment where you can see that happen. So the AB line is called the boiling point, all right? And it's the liquid vapor interface. And along this line, substances can be a liquid. The substance can be a liquid and a gas. It depends on the pressure and the temperature. Notice how the boiling point changes as the pressure changes. So as the pressure, so let's pick a pressure. Let's say, well, this is 1 atmosphere. I don't know what it is, but let's just pretend. This is 1 atmosphere, okay? So at that point, I can see, well, here's the boiling point, right? Here is the point at which the liquid would become a gas. But as you increase the pressure, right, you've got more pressure of the atmosphere pushing down, actually, I'm sorry, we're talking about a liquid here, pushing down on this liquid and keeping those molecules relatively closer together. So in order to get it into the gas phase, you would have to increase the temperature so that you would increase the kinetic energy of those particles so that they could break free of their intermolecular forces. As the pressure gets higher, the boiling point increases. And that's just what we just talked about, right? So as you are putting pressure on these particles, then it's going to take more and more kinetic energy to be able to break those molecules or atoms away from their intermolecular forces and become a free gas. So I think I just explained that, and hopefully you understand that. So the AD line represents the melting point, okay? I can tell it's a melting point because I have solid and liquid, right? And so the melting point does not change very much at different pressures. And let's think about this, right? So let's say this is 1 atmosphere of pressure right here, okay? And so then I can say, okay, well, there is my melting point, all right? So now as I increase the pressure, notice that my melting point doesn't really change that much. It's not like what we saw with the boiling point. And that should make sense to you, right? So as I'm increasing my pressure here, the transition from a solid to a liquid, I don't need that much more energy to get the molecules to have enough kinetic energy to move enough just to break the very strong intermolecular forces that we have in a solid. Along the AC line, we have sublimation. So these are usually at very low pressures. It's usually impossible for the substance to exist as a liquid. So at very low temperatures and pressures, sometimes you just cut out the liquid phase. This is particularly true with a substance like carbon dioxide that has very little intermolecular forces. It certainly doesn't have any hydrogen bonds like water does. And so you're going to go straight from a solid straight to a gas. So here is carbon dioxide, okay? So we've got this carbon dioxide. Remember, this is a very nonpolar molecule. And let's look at what temperature can carbon dioxide exist as a liquid. Well, it can. Here it is way over here, but notice that it would be very high pressures. My goodness, atmospheric pressure is where we are right now. Atmospheric pressure is approximately what we are in York, Pennsylvania. And so look, in order to even see carbon dioxide as a liquid, I would have to have 5 times the pressure that I have right now on me. I would have to increase it to 5 atmospheres to be able to see liquid. So this would be my triple point, right? This would be my triple point right here. Notice it's a pretty low temperature, right? Below freezing. And over in here, so this is my supercritical point right here. This is where at this point and beyond, I would have something called a supercritical fluid, which we'll talk about in just a minute. So at what pressure will it no longer sublime? All right, at what pressure? Well, here is sublimation, right? Because I'm going from a solid to a gas. So subliming, subliming, subliming. But here at that pressure and at that temperature, that's my triple point. Anything above that, it's not going to sublime anymore. It's going to actually go through the liquid phase. What phase is it at 0? So 0, I'm guessing, is maybe right about here. And 4 atmospheres, so 4 atmospheres maybe is right about here. I'm just guessing. So I go here and here. It would be a gas, all right? At what phase is it? At minus 62 and 10 atmospheres. So let me get rid of some of my scribbles here. All right. And let's take a look at this. So I've got minus 62, so I'm right about here maybe, and 10 atmospheres. So 10 atmospheres would be maybe right about here, 10. And so I can see that would be a solid. All right, so now let's look at these different phases. And let's see if we can recognize our melting point, our boiling point, and our triple point, and our supercritical point, right? So anything above, let's take our supercritical point, and this is water, all right? So we're going to talk a little bit about water, and we know water because water is ubiquitous around us, and we understand water very well. So because we have a lot of experience with it. So here's solid, this is liquid, and this is gas. okay? So at a supercritical point, way up here at D, at this point and beyond, in this phase up here, we would have something called a supercritical fluid. And a supercritical fluid, I hope you have a chance to play with some of that when you're a chem major someday, but supercritical fluids have characteristics that are part liquid, part gas, kind of somewhere in between. And they act very strange. They have a density more like liquid, but they have a diffusion ability more like a gas. So they're kind of cool. But anyway, the supercritical point, the critical point of water is, you can see 218 atmospheres. That is a lot of pressure. And it's actually 300 degrees C before you would see a supercritical fluid of water. So we don't usually see that. Our melting point, right? So here's our melting point. So melting point, let's see if we can find it. I want to go from a solid to a liquid, and about 1 atmosphere, right? About 1 atmosphere is where we are here. So in York, I know that at this point, this line at B is about 0, right? And here, well, what is the boiling point? Well, I know boiling point is 100 degrees. Here's liquid, here's gas. Again, here I am about 1 atmosphere pressure in York. So I'm going to go across here, right? And here is the interface, right? Here is the interface. This is the interface between my liquid and my gas, my boiling point here. And so at that pressure, this must be about 100. All right? So you can calculate what these things are. Now, this point, I know, is the critical point. I'm sorry, triple point. Sorry, triple point. Because it's between the solid, liquid, and a gas. And notice that this is going to be less than an atmosphere, right? And it's going to be just a little bit above 0. So I want you to look, I mean, water is really weird, and I want you to, but you don't really notice that until you compare it to some other substances. So here's a typical substance, and I can see this is the phase change diagram. And I want you to look at the phase change diagram of water and compare it to a typical substance. And I'm going to give you just a minute and see if you can figure out what specifically is different about it. So one of the things I hope that you noticed is the melting point, all right? Notice the melting point of a typical substance has a positive slope right here. Look at water. Water has a negative slope here, right? It's almost like going backwards there. Notice that the boiling point, right, the line here, up to the critical point is very similar. So it's that melting point that really makes water different. So let's see if we can figure out why this is, all right? And remember, this is pressure, this is temperature, okay? So this is temperature, this is pressure. And normally, as you increase the pressure, right, as you increase the pressure on the solid, you're going to have a greater and greater temperature to get it to melt, right? As you go up with pressure, you're going to have more kinetic energy for my molecules to get it to actually break loose. But water is weird. And one of the reasons why is because water has such strong hydrogen bonds. And I almost think that you might understand this a little bit better if you think about water wanting to stay in a liquid and resisting going to a solid. And think about this. Water has very strong intermolecular forces. That means the attraction of one water molecule to another water molecule is very strong. Okay, so here is my It's very polar, right? So that means if I have another water molecule, right, then I'm going to have some hydrogen bonds between this partial positive end, the hydrogen, and the partial negative end of another molecule, right? So they're very attracted. It pulls them. And as it turns out, water can actually get closer. The water molecules can actually get closer in a liquid than they can in a solid. And we know this because we know that the density of water is actually greater than the density of ice. Well, what does that mean? That means that in ice, the H2O molecules are actually a little bit further apart. So that explains why this slope line here actually goes to the negative, right? It's almost the reluctance of water to go into a solid because it can actually get closer if it's in a liquid. So here is a picture of the crystal structure of water, and the water molecules, when they make these structures, their intermolecular forces are in place, of course, to hold them there in this crystal structure, but they actually can't get as close as what they could do if they were in water. And so that is why H2O solid has less density than liquid and it floats. So, one final question. Does water always boil at 100 degrees? You should be able to answer that question. All right. Hope this has been helpful and see you in class.